And we're live. Hello, everyone. Thank you for the audience for coming out, and thank you to Dr. Long for being with us today. We'd like to thank, before we get started, the University of Central Arkansas Foundation for its support of this seminar series. There will be a Q&A session at the end of the Hangout. Also, you can use the hashtag #GHOSeminar on Twitter to submit your questions. And we're live. Hello, everyone. Thank you to the audience for coming out. Thank you to Dr. Long for being with us today. We'd like to thank, before we get started, the University of Central Arkansas. Okay, sorry about that. Anyway, our speaker today is Dr. Elena Long, and she is going to be speaking with us about understanding the nature of normal matter. Just a quick background about her. She got her BS in physics at Juniata College and her master's and PhD at Kent State University. Now, she is currently doing a postdoc at the Jefferson lab. She does research focused on the internal structure of nucleons. So without further ado, I'd like to turn it over to our speaker for today.
All right, thank you very much. I'm excited for this opportunity. And I'm going to go ahead and share my screen now. So hopefully, if I start this, you can all see it. Can you all see that okay?
Yes, we can.
All right, perfect. So as mentioned, we're going to be talking a little bit today about understanding the nature of normal matter. So there's this kind of blobby picture up here on the upper right-hand corner that hopefully by the end of the talk today we're going to understand what's going on here. So we're looking at like individual nucleons as these big blobs. So these are like protons and neutrons inside of a nucleus, and then each of these are made up of tiny smaller bits, and they're interacting with each other. And we'll go into detail of that a little bit further. But first, I want to mention just kind of a little bit about me. Just kind of continuing the introduction already. As was mentioned, my career path, I started out in Pennsylvania. I grew up in rural eastern Pennsylvania and didn't move far going to my undergrad college, which was Juniata, where I got my Bachelor's of Science in Physics. I then moved out to Kent State University to start my grad school program. And I spent 2 years out there doing my classwork and doing my candidacy exams, and after that, I actually moved down to Virginia and had the opportunity to work at a national laboratory down there called Jefferson Lab. It's an electron accelerator that I'll talk about a little bit more detail in a little bit. And I also want to mention kind of a little bit of my unpaid career path, I like to call it, which started roughly around this time. In 2009, I founded an organization called LGBT plus physicists to meet the needs of lesbian, gay, bisexual, transgender, and other sexual and gender minority physicists. We put together this great best practices guide for supporting LGBT plus physicists and astronomers. So for anybody interested, you can find that on our website. 2011-ish, still in grad school, I also joined the National Board of OSTEM, which stands for Out in Science, Technology, Engineering, and Mathematics. And we just had our 4th conference, which this is a picture of one of our keynote speakers, Lynn Conway, talking in front of our audience of nearly 500 students. And for any OSTEMers watching out there, we will have our next national meeting in November 2015 at Carnegie Mellon University. So this is kind of some of the stuff I started working on in grad school. I'm still working on both of these, but now I'm a postdoc at the University of New Hampshire, so moving way up in the fold of New England. And up here, I'm continuing both my physics research and also kind of the unpaid career path. We've recently just started with the American Physical Society a ad hoc subcommittee called the Committee on LGBT Issues, or CLGBT. And for those of you who get physics today, this came to my mailbox this morning. If you look at page 25 of that, we actually have an article that goes into a bit more detail on what CLGBT does. So if you're interested in that, go read that article. But at this point, I think that's enough about me. Let's start talking about the physics. So an overview of what we're going to be talking about. We're first we'll go over a little bit of a sense of size so we can start really trying to understand just what we're looking at and how small these bits of matter we're going to be looking at are. We going to look at how we do electron scattering experiments and a little bit about why those are important, and how we're going to use them to determine nucleon structure. So this will be split up into a couple different parts. The first will be electromagnetic form factors, the next will be structure functions, and then the next will be kind of the future of understanding nucleon structure through tensor polarization, which is what I'm working on now. So we start with the structure of matter. We'll start talking in the order of atoms, which are roughly an atometer, 10 to the minus 10th meter in size. And they have electrons going around the outside and protons and neutrons on the inside. So if we zoom in on just the nucleus, this is starting to get into where I find things being interesting. These are on the order of 10 to the minus 14th meters. And then if we go into individual protons and neutrons, we're down to a femtometer, 10 to the minus 15th. And the game doesn't end here. Protons and neutrons are made up of smaller parts called quarks, and as near as we've been able to determine, they're point particles, which is to say we've put an upper limit on how small they can be. But they seem to be point particles at this point. Same thing with electrons. We can put an upper limit on their size, but we can't quite find their actual size. So this is kind of a brief overview of how we're going down, and I want to click on this little link here to help get a sense of the scale, because just clicking on, or just pulling up those numbers, I think it's a bit hard for me to get a grasp on. So hopefully I can throw this up and it will work. So this is a great little app that was put together by Carrie and Michael Hong that basically looks at the size of the universe, and you can zoom in and out. So starting roughly human size, about 1.5 meters, we can start zooming in and start seeing like meter sticks, ostrich eggs, cups, things that are really familiar size, chicken eggs, and Rubik's cubes. And we start being able to see wavelengths of light around the centimeter. So these are microwave wavelengths. Start getting down to coffee beans, start getting into bugs and sesame seeds, and really just zooming way in. The millimeter range, we start seeing salt crystals, we start seeing the size of an individual computer pixel, but this is still far too large for what we're looking at. We're going to zoom way down. We start getting to individual cells and some of the larger viruses and what the wavelengths of light are, of visible light. And that's at about 10 to the minus 6 meters or micrometers, which once again, far, far too large, so we have to dig deeper and deeper. If we start getting to the size of DNA and carbon nanotubes, and we start being able to just be able to see some of the largest of atoms, we're in the nanometer region. So nanotechnology right now is dealing with things of this scale. So it's a really big field right now, but as far as I'm concerned, it's far too big. So we dig down even further, start going past X-ray light and gamma ray light, and really beyond this point, we can't use light anymore to look at what's beyond this level, because everything smaller than this, and you see this point way down there, is just too small for light to see. Light just goes right on by it as if it's not there. So if we zoom way in on that, we're looking at this 10 to the minus 14th, which is starting to get interesting as far as I'm concerned, because now we're starting to get into nucleus of an atom. So we have protons and neutrons in here. They're at about 10 to the minus 15th meters. And way in the center of that is a tiny little dot that if we zoom way in, these are the upper limits of quarks I was talking about at the 10 to the minus 18th, roughly, meters. So really, really small things we're talking about, and to kind of bring that back up, we throw that back inside of protons and have the protons go back into atoms, and then the atoms start making molecules, and then the molecules start making cells, and then the cells start making organisms, and then finally we really get back to the level that we're familiar with. So really, really small is the point I'm hoping to convey. So let me find where my talk went, and hopefully that can come back. So I mentioned we can't see these things with light because it's just way too small to see something with wavelengths of light. So the way we look at it instead is through a technique called electron scattering. So for electron scattering, what we do is we have some kind of target material, and we shoot electrons in at it. The electrons bounce off, and we count them in a detector. You can kind of think of this like a really advanced game of table hockey, where the electrons coming in are going to be the puck, and the target's some heavy nucleus, so if you put your hand on the puck, it becomes a lot heavier. And we shoot the electrons in at high speed, which you can feel recoil your puck, and when the puck goes into the goal, that would be similar to going to the detector, and we really start counting how many electrons go into the detector the same way we start counting score in air hockey. So some important quantities that are going to come up over and over again throughout the rest of the talk. The first is a quantity called nu, which is the energy transfer. So it's basically looking at the difference in energy from the incoming electron to the energy of the outgoing electron. And what that tells us is how much energy gets transferred to the target nuclei and gets shot out the other side. So even though we're only looking at the electron, it can give us valuable information about these interactions that go on. The other important piece I want to talk about is called Q squared. It's our momentum transfer. And for the most part, you don't have to worry much about this except to know that it's related to both the energy going in, energy going out, and this angle going up into the detector. And it's related to the resolution of our detector. So as we go up to higher Q squared, we get better resolution. We can see things that are smaller. And that's going to be important down the line, so keep that in the back of your head as we move forward on the talk. The next quantity I want to talk about is this quantity x, which is a momentum fraction of a scattered particle. So we have our form momentum up here, this q squared, and then mass of a proton or neutron. They're roughly the same mass, so it doesn't matter which you use, times nu, our energy transfer, is really scaling this, the momentum that we're knocking things out, to the momentum of a single proton or neutron. So we can use this to start looking into different energy regimes. The first one I want to talk about is elastic scattering. So if we have this x being fairly large, so x of 2 or greater, what we're able to do is start probing nuclear effects. So what we see when we do this is a sharp elastic peak that'll appear when we start hitting the nucleus, and then nuclei will start resonating. Different particle resonances will happen shortly after, which are these little peaks here. And this gives us some information about the nucleus as a whole. So when we talk about the x greater than 2 range, we're really probing nuclear effects that are a combination of the entire nucleus. If we change the region we're looking at and go into about the x of about 1 region, we call this quasi-elastic scattering because we're knocking out a proton or a neutron, but we're only kind of hitting just the proton and neutron, not getting any deeper than that. So it's like elastic for proton and neutron, but it's quasi because it's knocking it out of the whole nucleus. And when we do that, we add to our plot up here, we see this broad distribution peak that you get when you're knocking out 1 proton or 1 neutron. The reason it's not as sharp as this elastic scattering of the nucleus, why it's more spread out, is because it's interacting with all these other nucleons in here. And that interaction tends to spread out these peaks. So if we hit it with just a proton without any more nuclei, you'd see a sharp peak as well. But for the most part, we'll be looking at hitting nuclei and knocking themselves out, so we'll see a broader peak. The last region I want to talk about is deep inelastic scattering, which is the small x less than about 0.7. And then you start seeing similar resonance effects that we saw with the nuclei, and this is where we can really start getting to the region where we're probing quark effects. So there's little bits of matter that are inside of protons and neutrons. We can start really looking at what they're doing. So I'm going to be referring back to elastic scattering, quasi-elastic, and deep inelastic scattering as we go through the rest of the talk. So a place where we do kind of work is at Jefferson Laboratory, which, as I mentioned, is in southeastern Virginia. This is an overview, an overhead aerial photo of our laboratory. It's a fixed target electron accelerator, so instead of like LHC has 2 protons going around smashing into each other, we fix a target and then just accelerate the electrons and shoot the electrons into the target. We recently completed a 12 GeV upgrade. That's our energy level we define the lab by, which doubled the energy, and it's just turning on, which is really exciting because we're getting our first new physics in quite a while. It's a world leader in polarized beams and polarized targets, which we'll talk about in a little bit. And this is part of the mission, which is really to look at discovery caliber research by looking into atomic nuclei and the bits and pieces that make it up. So underneath here is about a mile-long racetrack, and along this racetrack are two straight portions. These two straight portions are where electrons coming in get accelerated, and then we bend them around these curved parts to feed them back in. So it's really like one linear accelerator, bending, second linear accelerator, and bending. And we can go back and forth in this 5 times. After we get the electrons up to the energy we're interested in, we can shoot them into one of 3 experimental halls. There's actually a 4th hall D over here that was just built, but I'm going to focus on these 3 down here. So this kind of detector scheme I mentioned before, if you look at that in the lab, here's a picture of one of these detector systems, and if we put a person next to it for size, I really want to impress on you how big machines we need to look at such tiny bits of nature. So these things are roughly 6 stories tall and have about the footprint of a mobile home, and you can kind of see they're on these big train wheels, so we can actually spin these things around in a circle. So where these big detectors sit, if we rotate that down and throw it down in one of these experimental halls, is way down there. But this whole thing is about a mile in diameter. We have our electrons come in, and like I mentioned, get accelerated around, and then go into one of the experimental halls, hit the target, and go into the detectors. So we can use this kind of machine to start measuring the structure of protons and neutrons, which is what we're interested in. So what we use for measuring this stuff is a quantity called the cross-section. So think of this as like a normalized amount of counts. So n would be the number of counts we're looking at times the luminosity times time times your cross-section. So if we go back to this simple drawing, every time an electron goes into the detector, that's giving you a number of counts. You're just kind of ticking away at it. The luminosity term's a bit different. If we have the number of electrons coming in and the number and density of atoms being large, these terms together give us our luminosity. It's basically how likely you are to hit something given a certain set of conditions. So if you have a higher beam current, more electrons coming in, you can bring the luminosity up, or if you make denser material, you can make the luminosity go higher. So that's this little script L is for our luminosity term. And the last one is time, because we don't want to, if we just count things forever in one setting, change it to another setting, count again, you'll get very different results in the number of counts just because you let one of them run for a longer time than the other. So we normalize for time as well. So the cross-section is, we just rearrange that a little bit, the number of counts divided by luminosity times our time. And this is what we can measure. This is what we observe. And we can utilize the cross-section to start telling us information about what's inside of protons and neutrons. So an important cross-section equation is this first one called the Mott cross-section. And this is a quantity that we get if we scatter an electron off of a point-like nucleon. So we assume that the proton and neutron we're hitting doesn't have any substructure to it whatsoever. It's just a big, heavy proton or neutron, and we bounce a light electron off of it. We get this simple scattering term. We can modify that by other things that kind of come afterwards, and I don't want to go into too much detail right in this slide, but any of these kind of equations after the Mott cross-section start telling us how protons and neutrons deviate from being point-like. So this really starts getting into the substructure of what makes up protons and neutrons. If we include something called polarized spins, which we'll talk about in more detail later, but protons and neutrons are both spin half, which is to say they can either be in an up state or a minus state. Then we can measure the cross-section in either the up state or the down state by putting our target in one of these states or the other. And looking at the difference in cross-section between those, if we do the number of counts up and the minus, subtract the number down and divide that by the total, we call that an asymmetry. And that's related to the cross-sections being in the up and down states. So when we do any kind of these nuclear physics experiments, the two things that we can measure are the cross-sections or asymmetries. So any other kind of theoretical model that we want to use to understand what the fundamental structure of protons and neutrons are doing, we have to relate back to these experimental quantities. So one of the ways we use this is for electromagnetic form factors. We're starting off the same way. We're scattering electrons from protons or neutrons. We have this Mach cross-section for our point-length particle and this deviation term at the end. There are two pieces in here, this GM and this GE. The first one is a deviation that's caused by the magnetic moment distribution inside of protons and neutrons. And GE is a deviation based on the charge distribution. So if we go to a q squared of 0, remember this is the point where we're really looking at the outside of a nucleus as a whole. The charge distribution for the proton goes to 1 because it has a charge of 1. And the charge distribution of the neutron goes to 0 because it has a charge of 0. And the magnetic are similar except that they go to the magnetic moments for the proton and neutron. So kind of keep in mind as we go through that as we go to higher q squared, that means that we're doing better resolution. And if we see any changes with q squared, that's indicating some kind of underlying substructure. So let's start with a simple experiment. We take a hydrogen atom, which is just one single proton, and we scatter an electron off of it. The nice thing about dealing with protons is that they're charged, so we can use normal spectrometers to isolate and measure the cross-section or asymmetries with them. By normal spectrometer, what do I mean? The most important piece is a bending magnet, and what that does, if you have a charged particle going through a magnetic field, it will bend. We send the bent particle into a detector, and since we're bending it, we can tell other information too, like the momentum or how much energy it's depositing. We also just have some focusing magnets that work similar for charged particles that lenses do for light. They just make sure that we know exactly where things are going in our experiment so that we can measure things well. So the proton would go into these, bend in the magnet, and get picked up in the detector, and that gives us a bunch of information about what's going on in the proton. So once again, here's a picture of one of these with a person being fairly small. This big piece in here is the bending magnet. There are two focusing magnets here and a third one here. And this big white hut up here is our detector hut with a variety of different detectors in it. So we basically run this for a while, count the number of particles detected. That gives us our cross-section. And since we have two unknowns for the proton, we have the electric and the magnetic form factors. We need to do two different measurements, and then we can solve back for them, just simple algebra. And as I mentioned, there's a relatively easy experiment. So here's some older world data for the proton form factors, which fit along this nice curve here, and it looks very pretty. But I do want to mention again that as we go to higher q squared, that changes our resolution. So when we're at low q squared, it's elastic. When we're roughly a q squared of 0.5 to 1, we're in quasi-elastic. And as we get to much higher q squared, we're probing quark effects. So for ease, since we have this nice kind of curve going on here, we can compare this to electric and magnetic dipoles. So a dipole would be like a normal bar magnet. It has a north pole and a south pole. It has two poles. And if you would take something like this and put it on a plot that you would look at its form factor over its structure, it would give you this nice curve here that would go up to 1 if you normalize it properly for the magnetic form factors. And it goes down very nicely, very exponentially, and matches up with the data. So if we expect something to be dipole-like, then if we take the data itself and divide it by this curve, it should be 1. It should be unity. And that's how we look at data kind of currently. So bringing this kind of older data into how we show data nowadays, since we're looking at the difference between the electric and the dipole, or the magnetic and the dipole, we're seeing these being right about 1. So everything's making sense at low q squared. And as we start getting out to higher q squared, you start seeing this deviation from 1. So there's some kind of underlying structure of the proton that's coming out in this higher q squared. It's less so for the magnetic, but it's still kind of bending downward. And I do also want to mention that there's this discrepancy in the data. These black solid points are more recent polarized measurements versus these blue open points, which are older unpolarized cross-section data. And these were recently reanalyzed and showing some trending downwards, and all the current theories that are being put on these are really following the polarized cross-sections going down. So we think that just due to the way we measured things slightly differently, the discrepancy, we kind of theoretically understand that it's really dipping down as you go to high q squared. So what's this mean? We're getting some kind of underlying structure. How can we kind of get our heads around that? The way we do it in nuclear physics is we take a Fourier transform, which is a tool that lets us go from momentum space, like our q squared, into position space, which makes a bit more sense intuitively and in spatial position. And what we find with this, if we do this Fourier transform, is that towards the center of the proton, so this is the radius, and this is a charge distribution. So right in the center of the proton, you have a nice big positive charge. And as you get further away from the center, the positive charge kind of goes away, but always stays positive. So to put that in a cartoon form, we have a big positive charge that kind of dies off as you go towards the end, which isn't terribly surprising. But something that's a bit more surprising is if we start looking at the neutron. So the neutron gives us trouble. The first part of trouble it gives us is that the electric form factor of the neutron is much smaller than the protons. So the proton falls along this curve up here, but the neutrons falls way down here. So it's extremely tiny compared to the proton and its flipping sign. There's interesting structure going on there. We also have a problem in that we don't have a free neutron target. So we have a free proton target in hydrogen, but we don't have a hydrogen equivalent for neutrons. So what we have to use instead is either deuteron, which is 1 proton and 1 neutron, or helium-3, which is 2 protons and 1 neutron. The deuteron is nice because it's not as bound, so you don't get as many nuclear effects. And the helium-3 is nice because you can do interesting spin cancellation, which I'll get to in a minute. So this would be kind of what we're looking at here, and this would be a quasi-elastic region if we're knocking out the proton. But since neutrons are neutral, we can't detect them using standard spectrometers like I showed before, because you can't bend a neutral particle in the magnetic field. So how do we look at these things? The way we do it is we build neutron detectors out of big blocks of plastic scintillating material, and these scintillators have a property that if a charged particle goes through them, such as a proton, it will send off light. So if we send a proton through, you'll see triggers come out, signal come out of every bar that the proton goes through because it leaves a light trail behind it. And that's a property of this plastic material. And the way we use this for neutrons, if we have a neutron go through this, it doesn't give off any light. We don't see any light going through it. So the way we tag neutrons in a detector like this is that we fill the whole thing up with protons. So it's plastic, so it has all these big proton carbon chains going in it. And as a neutron comes in, it'll start not hitting anything, then hit a proton, and that proton will leave a trail behind it. So our real signal for knowing we have a neutron is if we don't see anything before but do after, then that indicates a neutron. And in particular, if we very specifically look at these bars kind of surrounding the bars afterwards, if we see nothing in any of these but something after, that tells us we have a neutron. That's kind of our smoking gun for a neutron. We use that in our neutron detector to count how many neutrons we're looking at. And we can do a double cross-section measurement, which means we're counting both the number of electrons and the number of neutrons in coincidence with each other. And we use this in an experiment to measure the electric form factor of the neutron, which I was involved with when I was in grad school. This simple overview is not really what we use in an experiment. There's a lot more going on. So all these detectors out in the beginning here are really understanding what the electron coming in does. This piece out here we'll talk about a bit more, but this is basically that big bending magnet, the focusing magnets in the detector, and then this would be one of these neutron detectors I just talked about. Next thing I want to focus on is our target. I mentioned we can use polarized helium-3 in order to do some of these measurements. The neat thing about helium-3 is that it's made up of 2 protons and a neutron, and the spin of the protons will cancel each other such that the neutron carries a spin of the entire nucleus. So if it's in the nucleus is in a spin-up position, the neutron's aligned with it, and we can use this in an asymmetry measurement. So if a neutron's aligned with it in an up position, we can measure this and up. Or if we spin it down, again, the neutron's aligned with the whole spin of the helium-3, and the protons are canceling each other, which gives us this end down. And we can do it back again, do this measurement back and forth, and pull out an asymmetry. The bad part about helium is that there are these other states that exist in it as well. The S state makes up roughly 90%. These other make up about 10%. And if you're really interested in more of that, feel free to look at my PhD dissertation, which goes into detail of looking at these effects. But that's only going to be a footnote for this experiment, for this talk. This is what one of these polarized cells look like. We polarize the material in this big glass ball up here, and then let it just kind of diffuse down, and we shoot it with electrons down with these blue lines coming through. And here's just a picture of what it looks like in the target. So the electrons would come through, and the glass tube's a little hard to see, but it's right here, and things go out the other end into our detectors. This is, once again, that spectrometer we're looking at. I just want to flash through this quick. These are the different detectors in there. There's another picture of it, but we talked about that already. So let's go back to this picture of the neutron, and if we look again back at the electric form factor of the neutron, let's first zoom in on it, so we'll make that bigger, and then flip it upside down. And the reason I do that is because this is the convention we have nowadays for showing the data. So we'll see this kind of bump and then kind of dying off. So you see this bump and kind of dying off. So this is the most up-to-date data on the electric form factor of the neutron. The first thing I want to mention is there's not nearly as much data here as there is for the proton because of how small and how hard it is to do these measurements. This is a measurement we did of about q squared of 1, which is going to be in a PRL hopefully in the near future. And if we do the Fourier transform of this the same way we did for the proton, we can take the momentum electric information and turn it into position information. And what's fascinating about the neutron, particularly as we go deep into it, is that it has this very negative core and then goes positive and then goes negative again. This is strange, right? This big negative core is kind of an open question of what's going on here. We used to think that the neutron could be thought of as like a proton with an electron kind of bound to it very tightly, although it'd be a pion bound to it that can decay into an electron through a weak interaction. But this really, the negative core is interesting and fascinating. It's an area of ongoing research of what's causing this. But if you take all this stuff together, what it's really telling us is that there's something inside of protons and neutrons. There's some substructure in here, and that the substructure is charged. So if we want to learn more about the substructure, we have to go into a different energy regime. So we do this by going into the deep inelastic region, which if we do measurements on this, instead of form factors, we call them structure functions. So again, we have our Mach cross-section, which is our point-like nucleon. We're scattering off of that. And then our deviation away from that. Our F1 and our F2 are our two structure functions I want to start talking about. And I'm actually going to start talking about F2, which has this plot here of the world data that exists for it at the moment. And if we kind of take the world data as it is and try to build up a theory of understanding it, hopefully we'll get a sense for kind of how we can build up a theory. So if we start with the Mach cross-section, we assume that the proton is just a single particle. So if we assume it's one quark makes it up, we would see a really sharp peak in X at 1. This doesn't go out to 1. The reason it doesn't is because it just dies off and is flat and is boring. So we don't see that, so we know it's not a single quark. Instead, it looks like it's peaking, I don't know, roughly around a third. So if you say we have 3 what we call valence quarks, roughly at a third, you should expect a really sharp peak right at a third. We're not seeing that sharp peak, we're seeing this smearing, and as I mentioned before, anytime we see a smearing, it's saying that there's some kind of interaction going on. If we throw interactions between these 3 quarks, it smears us out back and forth. So we're starting to get this high X part of the structure into our theory, but the low X part dies down in our theory a lot faster than it is in the data. So it looks like we have 3 interacting quarks, but that's not the end of the story. And if we add in what are called C quarks, these are quark-antiquark pairs that pop into existence for a brief moment of time, move around near relativistic speeds, and then go back into the void again in accordance to the uncertainty principle. If these are interacting with our valence quarks, or kind of more stable quarks we can think of them as, then what that does is really in this low X region bumps up this plot, and we call these the quark C. And now our theory curve is looking an awful lot like our data curve. So this gives us a really good indication that we can start understanding what's going on inside of the proton, and that it's made up of 3 quarks that are interacting both with each other, and with this quark antiquark C, these C quarks going on the outside. Keep in mind again that as we go to higher q squared, we should get better resolution, and if we don't see a change, there's no substructure. And a number of q squared from q squared of 2 to 18, which is massive, they're all plotted here in the same plot, and there's not really any distinction between them. So what that's telling us, that there's no distinction between us, is that this story of what's going on seems to be kind of the end of the line. But that only kind of tells us about what these things are, not what they're doing or any other properties about them. So this F1 gives us some terms about their magnetic interaction, which tells us about the spin. So if you have a particle spinning around, it's going to create a magnetic field. And if we do this in quantum mechanics, the only difference is it can only exist in certain states, these plus and minus states. And the definition for F1, if you have a spin half particle, is that if you take the difference, if you divide F2 from F1 and multiply that by your momentum distribution x, that should equal how much spin these things carry. So if they equal 1/2, then you have spin half particles. If they equal 1, you have spin 1 particles, etc. We rearrange this because we like showing data against 1, so it's the same equation, just slightly differently. And some data along that, hey, the data is fitting right along 1 when we do this. So what that's telling us is not only are protons and neutrons made up of these things, but that these things are made up of carry spin of 1/2. So these structure functions are really useful. This is the F1 structure function for the deuteron that's being used in a current experiment that's working on called EG4. And what we use this data for is to compare with some of these higher structure functions we'll talk about in a minute. And between looking at how different structure functions compare with the F1 and F2 structure functions, that can start telling us even more information about what's going on. It's an active area of research, and we utilize this with other pieces of information to get more information out. So from these two things, we learned that the nucleons are made up of 3 valence point-like particles, that these particles are spin half, and that they interact with a quark C. So the picture is getting a bit more complicated. I do want to mention from F1 and F2, we know they're in there, but we don't really know where they are. That requires more information. Luckily, we can get more information out of this. If we take, again, this mock cross-section with this F1, F2, we can rewrite it in a slightly different way with this W, which is a hadronic tensor, which I don't really want to get into much, except that this F1 and 2 come down, just a different way of writing the same thing. So if we have unpolarized nucleons, this W term has this F1, F2 that we're already familiar with. But if you polarize the nucleons, so if we polarize either the beam or the target, you get 2 new structure functions, these G1 and G2. So let's dig into these a little bit more. So in this case, again, we need a polarized target in order to start looking at these pieces of information. And our cross-section, if we have this plus plus sign, that says that our target spin direction is pointing in the same direction as the electron. They're longitudinal with each other. And if we spin the target around, we get this plus minus. So this plus state is saying the electron's spinning such that its vector is pointing to the right, and the minus would be spinning such that the vector is pointing to the left. And the difference between those gives us this difference in cross-section. And that difference in cross-section is neat because it's related to what the individual quarks inside the proton and neutron are doing. And that's what our definition for this G1 structure function is. So it's starting to be able to give us information in momentum about where valence quarks with a certain spin are located. And I want to point out this is the world data on this, of which there is a massive amount of data set kind of looking through this. And I don't want to go into these in much detail other than to say it gives us this information. And also that if we take this G1 information and divide it by F1, it can really start giving us distributions of where different flavors of quarks are inside of protons and neutrons. So if we take these ratios of G1 to F1 for the proton and subtract out the neutron, that gives us information about the up quark. And this is a recent paper that is here on the archive that shows the recent data for this, I believe, in these red points. It starts giving us information about where the U quark is. And likewise for the down quark, except you replace the neutron and the proton. So you take the neutron minus the proton, and you get information on the down quark. And this is the data that's existing for that. So not only are we able to understand that these things are in there, but now we can start trying to figure out where these things are inside of protons and neutrons. So using a polarized target and this G1 structure function, this starts being able to tell us where quarks of a particular flavor are and with a particular spin structure are inside the nucleon. I do want to mention kind of in this drawing here, I drew these spin half particles such that it looks like they cancel out so that one of them lines up the same way that the helium-3 did. But that's not really the case. If you actually do these experiments and part of this world data set, one of the interesting things that come of it is that the quark spins we find only make up about 30% the spin of the entire nucleus. So we're missing roughly 70% of it that we're not sure where that spin's coming from. So we'll come back to that in a little bit, but that's known as spin crisis, and it's a big problem right now. So let's look at this G2 structure function. Unfortunately, there's not really a simple interpretation like this for the other. It tests a couple of models, one called lattice QCD and one called chiral perturbation theory that I don't want to get into details about. But what I do want to mention is that we can rewrite G2 as two parts. One we call G2WW, the other G2 bar. G2WW is really related back to this G1, so it's based on information that we're already looking at with G1. And the G2 is based on this H and this chi functions in here. What this starts giving us information of is how quarks and gluons interact, and also starts looking at some polarization distributions. So this is kind of the world data that exists for these 2 points, and these are projected measurements that we're expecting for the polarizability on the proton in an upcoming measurement that we have some grad students working on. So this starts telling us information about what the quarks are doing and what these interactions are doing, so our picture of what's going on inside protons and neutrons is getting even more complicated. Which brings us to what my big area of research is right now on tensor-polarized nucleons, tensor-polarized deuterons, and electron scattering from them, and what we can do with them, or what I see as kind of the future of this topic. The tensor polarization is different from the normal polarization I was talking about before, because for these we need spin-1 particles. So let's dig that down a little bit. For a spin half particle, like a proton or a neutron, they can either exist in this up state or this down state. But if you have a spin-1, quantum mechanics allows for a third zero state. So we have an up state, a minus state, and a zero state. So protons and neutrons are spin half particles, but if you have one proton and one neutron, you can add them together to get a spin-1 system, and that's what the deuteron is. It's one proton and one neutron in a bound system. So to tensor polarize these, you can tensor polarize things that have a spin-1 or greater case. And it turns out that if you start looking at these, the spin-1 actually changes the shape of the deuteron. So you can kind of imagine one of these being the proton, one of these being the neutron, kind of this peanut shape. And if they're both aligned up, they make this peanut shape. And if the proton and neutron are both spin aligned down, they also make this peanut shape. But if you're in this spin zero state, it's actually making, it's interesting, it makes a donut shape. So we look at the difference between these two shapes is really what we're looking at with tensor polarization. Vector polarization is really related to what I was talking about before, where we look at something in an up state and just subtract out the population in the down state. And for tensor polarization, we add the peanut shapes together and look for the difference between them and a donut shape. And thinking in terms of food, if we start with all peanuts, then this tensor polarization, this PZZ, starts at 1. And as you start adding donuts in, when you have a third across all of them, you should get PZZ of 0, and then it actually goes down to all donuts, giving you PZZ, tensor polarization of -2, which is different than vector polarization, because vector polarization can only go from +1 to -1. So this can go from +1 to -2. And if you're in +1, you have all peanuts. If you're in -2, you have all donuts. And if you're in any other state, you have some combination between. So how do we do this kind of polarization stuff? What we're doing in our lab is a technique called dynamic nuclear polarization. So let's start back with protons. We'll start with a simple spin half case. And what we do is we have a solid material that we start with. So we either use frozen ammonia or lithium deuteride or butanol or plastics, some kind of material. This is a picture of deuterated butanol that's frozen in liquid nitrogen, which is why everything looks a bit bubbly. And we'll set that material off to the side. We take that material and put it inside of a helium refrigerator, which drops the temperature down to 1 Kelvin. And I like being at the 1 Kelvin range because that means that we are colder inside of these helium fridges in the deepest, darkest regions of outer space, which are in a few Kelvin range, which I find really fascinating. This picture on the top is really the inside and the guts of it. We feed we feed liquid helium in here, which is at 4 Kelvin, and then we pump on it using, so we enclose the whole thing up, fill it up with 4K helium, pump a vacuum on it, which causes it to evaporate. And then the same thing that if you have water on your hand and it's evaporating, it cools your hand down. That same process happens for the helium, so we evaporate it to cool the helium from 4K down to 1K. And that's how we get the material down to the temperature we need it to be at. If we then take that now really cold temperature and put it inside of a large magnetic field, and for us, a large magnetic field means 5 Tesla or larger, that gets us to our next step. So this is a picture of our solenoidal magnet that we use. This yellow wire running across it is superconducting wire. That whole thing gets dropped down into this big blue cryostat, which we fill up with liquid helium. And you can see us, this is my PI and our 2 grad students working on cooling down our magnet and testing it. And you do that, you just get you get it cold enough and you get a superconducting magnet around it. You have polarized electrons, which is great, but we want polarized protons. So to transfer the polarization, we include a millimeter wave generator. So this is that same kind of technology they have in the airport. When you walk in, there's the little yellow footprints, and you have to put your hands over your head. They have one of these machines there, and we use it to move the polarization from the electrons into polarization for the protons. So if you let that build up over time, you start getting an abundance of protons all spinning in the same directions. We measure that with an NMR system, which is this little metal box here, and we have a number of readouts. And what we see is a plot like this. So this is the frequency versus voltage, and you'll see this peak happen when you start polarizing the protons. And the area under this curve is directly related to how many protons you've polarized. So we can take this, calibrate it, and as this area gets larger, then we know we've polarized more protons. So this is how we measure it. So that's the case for spin-half particles. We want to do tensor polarization, so we need spin 1. And our goal really is to get tensor polarization of 30%. These are some details target I don't want to talk about, but the first way of doing this is through brute force tensor polarization. And this is, if you have vector polarization, you get tensor polarization for free, according to this equation here, where P is the vector polarization, A is the tensor polarization. So if we want 30% tensor polarization, we need 60% vector polarization, which is hard to do. So brute force isn't going to be, we're going to hit this as hard as we can, but we're not expecting that to hit our 30%. So we add an extra coil around it so that we can introduce a radio frequency field and really start playing with these interactions. So this is looking at the different substates for our plus one and minus one peanut shapes and our m equals 0 donut shape. And as you transition from one state to another, because of quantum mechanical effects, they can only do so in very specific frequency bands. So going from the -1 to 0 is shown in blue. There are 2 energy bands for that. And from the +1 to 0 is shown in red. This is related to the Zeeman effect, and I believe that that's often a modern physics experiment that you might be able to do in your lab, and I recommend doing it because it's a fun experiment that you can really start getting to the basics of what we're doing in the modern physics class. So what we want to do for tensor polarization is manipulate these different fields and what can go into each. So when we look at that NMR spectrum, we get this little Batman curve, and these two smaller jumps that are happening correspond to these 2 bigger peaks, these 2 sharp ones, and the 2 larger regions go out to these shoulder regions. So what we do for hole burning is we really want to push down on these 2 regions, on one of these peaks and on the shoulder. And what that will do will stop one of these transitions from happening, so really fill up our plus and -1 states and start emptying our spin 0 state. So we can kind of start going into one state and not the other. This is a plot of what that looks like. So we shot down the end here. And when I say we, I really mean Dustin Keller and the University of Virginia crew. And they shot down the shoulder. And we're in progress still. They're in progress still of working on this and getting it working better. And our lab is kind of rapidly trying to catch up, and hopefully we'll be here in a year being able to help out with this effort. So when we do this, we put in an electron scattering, and then suddenly we go back to these structure functions. We get 4 more structure functions that come out of this. I just kind of briefly want to go through what's interesting about this. The first one is B1. And again, structure functions tell us information about what the quarks are doing. But what's interesting about B1 is that it's dependent on the polarization of the entire nucleus. So we're really being able, for the first time, to look at nuclear effects at the resolutions of quarks, which is really exciting. So what's also really neat is that if we don't have any nuclear effects, if the deuteron is just 1 proton and 1 neutron, 1 proton, 1 neutron, hanging out, no interactions, and this should go to 0. If they're bound, we call this with d-state admixture, they're still expected to be extremely tiny for this observable. So any conventional nuclear physics model, particularly out here at high x, expects V1 to be very, very small. At low x, it kind of shoots up because of this quark C stuff that we were talking about before, but this high x region is really what's interesting. So this was measured at Hermes, which is a positron accelerator, and they found a large negative value here, which was entirely unexpected. And in order to really understand this, we need to start looking at exotic physics. So these are two recent models that are trying to understand what's going on that we'll talk about extremely briefly. The first is a close Kumano sum rule. So basically, if you add up B1 times x over that whole region, they expect it to be 0. But if you have an unpolarized C, this doesn't work. This fails. So B1, they split up into the quark part and then the kind of C quark, which is these quark-antiquark pairs, although they're only looking at the antiquark part of that. If they leave it unpolarized, then this term here is 0, so that whole piece goes away. Or if you look at it polarized, and that's non-zero, and you have polarized antiquarks. And what they found is it wasn't 0, and it showed significant polarization in the quarks. So this dotted line here, this dotted black line, is what happens if you don't have the polarized C quarks, which doesn't really fit the data, as well as this red line when they start including the polarized C quarks. So now with B1, we can start getting information about what polarization of the quarks themselves is doing, and in particular these C quarks, these kind of ephemeral quarks popping in and out of existence and according to the uncertainty principle. We can also look at 6 quark hidden color models. So these would be things where the deuteron, instead of being just a proton, just a neutron, is really a big bag full of the stuff that makes up both of those. So it really kind of loses its information. So this hidden color piece is on the end here. We won't talk about that much. Early calculations of these effects gave small results, but the author of the paper in this theory has noted that the meaning of small has changed as our experiments have dramatically gotten better. And if you have an experiment, we have an experimental limit that says the probability that these effects exist has to be less than 1.5. And if you put something even tinier, like 10 times smaller than that in, you can still get a significant effect. So I don't want to talk about that much. Here's what the effect looks like. It causes a bump. And it's this bump down here that's actually starting to reproduce this data. They gave us calculations. We measure tensor polarized versus unpolarized, and we use that to get B1 by multiplying again to this F1. So this F1 is still really important. That plot's not important. We're going to do this in Hall C at Jefferson Lab, so the same kind of detector, and these are the results that we're expecting to get for it. So we're expecting to really bring the uncertainty bars down on these and really look at this crossing 0 point into here. So that hopefully will be running within a couple of years, and this should give us insight on the tensor polarized systems, this close Kumano sum rule. Didn't really talk about the orbital angular momentum part, but that comes into play, polarization of the C quarks. And really, this stuff starts getting really complicated. And then it gets even more complicated. We break it apart, really understanding the deuteron. If we take the same AZZ, which we use to measure B1, we look at the deuteron wave function here. We have these two kind of lines going down. This first one's related to this S state and the peanut structure, the other one to the D state. And this observable in the quasi-elastic region instead of deep inelastic is related to this ratio. And understanding this ratio at high momentum transfer is really important right now because we get these big deviations depending on the theory. You also see this deviation between this blue and this red curve. Those blue and the red curve are calculations being used to understand short-range correlations. For short-range correlations, you have an electron coming in, hitting a nucleus. You expect it to just hit the proton and go out, but 20% of the time, we're seeing a proton-neutron pair shoot out at high momentum in opposite directions. So 80% of the time it goes like what you would expect, and then 20% of the time you see these particle pairs going off in opposite directions. And the majority of that is proton-neutron interaction, so a deuteron, so it makes sense to look at this for the deuteron. And this really is what's looking at in this kind of picture I showed way in the beginning. So with looking at this tensor structure and the quasi-elastic region, it can really start telling us about short-range correlations. These two models are relativistic effects. And really, it gives us a better understanding of this ratio, because if we can't understand what's going on in the deuteron, how can we expect to understand anything bigger than the deuteron? And with this, we're really hoping to be able to understand this much better than we've been able to in the past. This was a very nice thing that our program advisory committee said about this experiment, which we're going to be putting forward as a full proposal this coming year, saying that it was well developed, enjoys strong theory support, and that it would further explore the nature of short-range proton-neutron correlations in nuclei, the discovery of which has been one of the most important results of the JLab 6GeV nuclear program. And I can't really end it on a better note than that, so in summary, we gave a sense of scale, started looking at the form factors, building up, showing how things get more complicated as you go into the tensor region, and I hope that I've given you a bit of an understanding of the nature of normal matter. Thank you.
All right, what a great presentation. All right, I'm going to pull up the Q&A here and see if we have any questions. Looks like we don't. So that'll transition us to our audience. Does anybody in the audience have any questions? John.
Yes. Early in your slides, you're showing a sigma mods. Which I think you said was deviation for your statistics, right?
The sigma mod is if you have a point like proton or neutron. So the proton or neutron, you assume it doesn't have any substructure. So all these complications, if you assume they're not there, we get them on cross section. The reason we utilize that is because it's really easy to calculate, and we can modify that by that other stuff going on after it. So if we multiply that other stuff by the Mach cross-section, that other stuff is what gives us information about the substructure.
Okay, yeah, because I was looking at that other stuff, and it looked a lot like a Hamiltonian operator. So,
Yes.
Yeah, okay. I guess that's what I was going to ask. So it had the right side of it, which is usually the potential. So is that just derived from the structures themselves?
Right, so what's going into there is we're kind of taking relations of how these things are interacting at a quantum mechanical level and building them up into these form factors or structure functions. And in either case, you can kind of think of them as trying to map out the internal structure of things. So we're trying to relate these things back to the cross sections, and the quantum mechanics is at the base of it. So we're developing through the quantum mechanical models these kind of slightly more complicated structure functions that are really telling us how we can map these things out. So it's kind of like if you take those basics in quantum mechanics, put them into a form that we can start using as a map, and then looking for the structure within that mapping.
Okay, that makes sense.
All right, any more questions? Yeah, Lucas. I have a question. I haven't been very formally educated on quantum mechanics, but you mentioned C quarks, and is that just basically like the background of the universe? Like it's just like when you see it, when you have a sea of ions, it's just like this background that you can treat as like an infinite potential of just things that you could reach in and grab, like a ground on electric current or something.
Right. So it's related to them, but we actually see a flux of them around the nucleons in particular. So actually, if you add up the mass of our valence quarks and look at the mass of a proton, the valence quarks only make up about 1% the total mass of the nucleon. Some of that extra mass, and 99% of the mass, most of it, is coming from interactions of the gluons being exchanged between them. And the rest of it's coming from these C quarks, these quark-antiquark pairs popping into existence, moving around near relativistic speeds, and then going back into the void again. That kind of flurry of activity seems to be centered around protons and neutrons, more so than the vacuum, but it's the same underlying uncertainty principle. The way that I'd like to kind of take that and put it down to a short sentence is that not only are we made up mostly of empty space, given the space between electrons and the protons and neutrons inside, not only are we mostly made up of empty space, but most of us that isn't empty space doesn't exist anymore, because it exists as this flux of energy and matter constantly popping into and out of existence.
That's a pretty good way of putting it. I like that expression a lot. Questions? All right, Dr. Long. So you said that there, well, in your abstract, there's been a large increase in sort of the knowledge of all of subatomic physics. In your opinion, where is sort of the future taking us?
Well, yes, I would say the future is taking us into tensor polarization, which is the stuff I'm working on, and it's part of why I'm working on it. What I think that tensor polarization does is start giving us information so that we're at the point of understanding now that we can get down to the quark level and see the quark and gluon interactions happening. And that's kind of the state of where we are now. So the next step moving forward is to take these interactions and start building back up into a nucleus and getting a whole nucleus based on fundamental principles of what quarks are doing. And tensor polarization, I think, is going to have a play in this because if we do it with a deuteron, it can really get us to understand the deuteron in a way that we haven't been able to before. And like I said in my talk, if we can't understand what the deuteron's doing, we don't really have any hope of understanding anything further on. So I think the next step for this is really understanding, finishing up our understanding of the deuteron, getting that well under control. And I think tensor polarization is the path forward for that. And then once we have the deuteron under control, we can start going to heavier and heavier things. And in particular, I very briefly mentioned the short-range correlations. I think understanding the deuteron is going to start telling us about this, and as we go to heavier nuclei, the short-range correlation piece of it is going to become very important. Because we see short-range correlations in all nuclei we've looked at, and it looks like it's actually being applicable now to neutron stars. So if we talk about massively large nuclei, the idea that it has a sharp core and then kind of a sharp neutron core and then protons on the outside, that kind of viewpoint is going away and giving view to more of a short-range correlation where the protons and neutrons are kind of spread throughout, and that there are just small correlated pairs kind of in this big spread out region. So I think by understanding this stuff in a deuteron, we can then start building back up into it, and I think that's really where we need to go from here.
Very interesting. Questions from the audience? I have a question. At the beginning of your presentation, you mentioned that you were involved with OSTEM. What is OSTEM? You explained. Could you elaborate on what that is? We have a STEM teach program here at UCA. I was wondering if it's like that or not.
Yeah. So OSTEM, as I mentioned, stands for Out in Science, Technology, Engineering, and Mathematics. So it's a chapter-based organization that is really trying to help out LGBT people, lesbian, gay, bisexual, transgender, etc. folks in the science and technology fields. There tends to be issues of isolation and whatnot within the STEM fields, and OSTEM came into existence as a way to start addressing this. So it's a chapter-based organization that has a national structure to it. So we have a bunch of chapters all across the country, which get run individually, and they bring in speakers and do like their own individual events. And then we as a national board, national organization, kind of oversee all of them, but they're kind of mostly independent. But we're able to every year bring them together for a national conference, and we're also able to provide speakers for them. We also interact with current events and going-ons that are influencing LGBT people in the STEM fields. Like we've been invited to the White House a couple of times to talk about how science and technology policies that are happening politically are affecting LGBT STEM students, and how some of these things we can work on some of these things to help make them better, to help make make life a bit easier for a population that's traditionally had it pretty hard.
Excellent. Thanks.
And if you're interested in starting a chapter, feel free to contact me afterwards.
Okay. Definitely make a note of that. All right, John, you have a question?
Yeah. I mean, I think you kind of answered it in the slides a little bit because I wrote it down early on. But I was asking before you talked about spin, how the spin of the electron in the scattering affects your measurements. Because when I saw you do the your ACE variable was, yeah.
Right. So it's a really good question. If we ever let's say our electron's spinning this way, so it has a vector that's pointing where my thumb's pointing, and we take a measurement where we have a polarized target spinning the same way. I don't have two of the same hands, so pretend they're spinning in the same direction. If we take measurements of electrons scattering this way, we'll get some count. And then if we flip the spin of one of them to make them anti-parallel, we can do the same measurement. And if we get a different number of counts when we change the orientation between the two, then that tells us something, some internal structure is going on, some spin-dependent structure is going on. So the reason why we're doing this kind of double scattering, we have a couple different ways of doing it. One is by having the electron and the target spins aligned or anti-aligned, and that gives us a difference. We could also do it so that our target spin is actually 90 degrees to the incoming electron spin, and then we can turn the target spin up and down. So when we say spin, we talk about spin and up-down, which is, I see a level of confusion on your face, which I'm guessing is going to this. The up-down spin states are in relation to the magnetic field they're in. So if you rotate that magnetic field 90 degrees, then you can make that go in a 90-degree direction. Because you still only have the spin up and spin down, you've just changed the magnetic field.
Right. I don't know. I think the way I learned it was weird. Because it confuses me how you can have something, because you said your target is stationary, essentially. Right. And how you can have something, and I guess you're just changing it, not measuring its spin. You're just assuming that the magnetic field makes it spin. Oh,
we measure it in a variety of different ways. I mentioned in a bit of detail the NMR spectrum when we're looking at the proton, how it kind of gave that big curve down, and as you get more protons spinning in the same direction, that NMR curve gets bigger. So we can relate that directly to how many protons are spinning in the same direction. So NMR is one of the big ways that we measure spin. Anytime you go in an MRI machine, you add imaging to nuclear magnetic resonance, and you have an MRI. So it's the same technology that's being used in machines like that. And one of the interesting things about nuclear physics as a whole is that our field is deeply connected to the field of medical imaging. Because we look at X-rays or CAT scans or MRI scans or PET scans, or there are recent helium-3 scans. So I mentioned helium-3 target. If you take that and breathe it in, you can actually get really good images of the lungs and actually see how the air itself is moving around inside of your lungs. So we're measuring the polarization, and these polarization measurement techniques turn out to be applicable very much so in the field of medical research.
Sorry. So when you guys are changing the magnetic, or the spin of the target, is that what you have, is a rotating magnetic field around it? Or, because I was assuming that resonance that would cause
So it depends on how your target's set up and what you're looking at. For the most part, we tend to have the field aligned one way, and we just kind of leave it there for a while. What is a while can change between 20 minutes to hours, and then we change the direction the current and the magnet's going in the opposite direction, so we can flip it from one way to the other. We usually let it sit there for one way for like 20 minutes to a few hours, collect counts, and then flip it and collect counts again. So that's how we're rotating the fields.
Okay. That's it.
Awesome.
I'm done.
Awesome.
I'm done bothering.
I have a question. So it's something that Dr. Slade usually asks in all of them is, if you could go back to your undergraduate level, what advice would you give yourself, and just kind of what are some of the things that you would think of and give us as advice as undergraduates looking for a career inside?
I think the biggest piece of advice I would give is really try and, if you're able to, get an understanding of what you would like to be doing a few years down the road from now. Trying to imagine your future is something that's difficult at any age, but when you're in college, it's really hopefully the time when you're starting to figure it out. And the reason I say this is because grad school is a massive investment of time. 2 years for classes plus another 5+ years of doing the research and writing your dissertation. I mean, that's 7 years that you could spend building a career elsewhere if you wanted to. So if you're interested in going into research, which is something that I've been interested in and have been following because I get to play with machines like the ones I was showing you, and I love the work, absolutely is worth it. But if that didn't interest me, if I wasn't kind of as in love with the work as I am, then going through all this and wasting that much time on something that wouldn't be particularly apt for me, don't do it. Grad school is not right for anyone. And I listened to a couple of previous talks. You mentioned how the job market in academia is rough right now. I think roughly only 1 out of every 8 PhD applicants will get a job within academia. So kind of keep this in mind. Like, this is kind of the state of the field as it is right now. It's very competitive, and all of you in the audience will have a shot at it, but it's a small shot. So if it's something you want to go for and it's something you think you have a shot at, absolutely do it. But if it's something that you're not as interested in, or if you're more interested in, let's say, making lots of money, then maybe physics PhD program isn't quite right for you.
Yeah, that makes a lot of sense. Just because we recently had a trip to Fayetteville with a class of mine, and yeah, they were talking about academia and grad school, and there was a professor there that happened to be talking about his wife who got a PhD in one of the sciences, but then actually got a law degree as well, and went into just getting a lot of money from that. And so that's just there's a lot of money to be made out there in the industry, but not to say that research isn't fascinating, because I do research here, and I think that's absolutely wonderful, but it's just I'm not sure that grad school would be a worthy investment of 7 years. So I guess I'm a junior right now. When did you really know that you wanted to go into academia and that you wanted to go into the research of it?
Very late in my grad school career. Not following the advice. That's what advice I would give to younger me, and that would be it. I actually took a slightly different path of going through undergrad. So I mentioned growing up in eastern Pennsylvania, and I grew up in a very, very rural neighborhood where everybody grew up and pretty much did what their parents did. So when I went off to college, I wasn't entirely sure what I was going to be doing. I actually was hoping to get into making special effects for movies and doing CGI work and working for Pixar. So I took a whole bunch of digital media classes and a whole bunch of physics classes, because we're talking about the time frame of like the first Toy Story movie. So computer graphics weren't quite where they are today, and I was hoping when I went to undergrad to get them to where they are today. And when I was in undergrad taking physics courses, I realized that physics was really interesting, and particularly when I started taking quantum mechanics courses and modern physics courses and understanding how weird the fundamental structure of nature is, and that you can go out there and you can measure it and you can start looking at how weird it is. That just kind of really turned me on to physics. And so I dropped the digital media stuff and really focused just on physics, just kind of thinking, oh, well, go get a job somewhere doing something, not really having a sense of it. My senior year, it's late my junior year and into my senior year, my advisors at the time were like, hey, you're doing really good in your classes. Are you considering grad school? I had never known anyone who went to grad school before. If you go directly back in my family, I'm the first of our family to graduate from a 4-year college. So grad school hadn't really occurred to me. So once they mentioned it, I was like, oh, maybe I should look into this. And what particularly drew interest for me is that for physics, they will often pay you to go to grad school. So they'll cover all of your tuition and give you a living stipend on top of it. And that pretty much is what sold me on grad school. So I went off to grad school, still kept being interested in the kind of the quantum stuff and the really small stuff. Passed my PhD qualifier, which said I can go on and keep doing research. and then got offered the opportunity to move to the beach in Virginia and go work at a particle accelerator, and I said yes, absolutely. So I jumped into that, and I think it was really when working in the National Laboratory and doing the work down there when I made the decision that I really wanted to keep doing this. Part of that, I do want to mention another piece of advice that I would give too. This is the same time that I started the LGBT plus physicist group, and one of the things that's really helped keep me in the field is having community. And for me, it's meant LGBT community, but for anybody entering these fields, it's hard, and there's a lot of things going to work against you. The field's competitive, grant funding is down, the government who you're funded by is doing what it's doing, and it makes it difficult. So really, building up a community of people that you can relate with and talk to and are comfortable with is absolutely imperative, not just for physics, but for any field you're going in. Really make sure that you find your people and connect with your people, whoever they may be.
That's awesome. So are there any more questions? All right, well, with that, I think we'll end the broadcast, and let's thank our speaker, Dr. Long, one more time.
Thank you all for taking time out of your evening for this.
Thank you. Yeah, we very much appreciate you coming in and giving us a talk. We really enjoyed it.
Great.